we can measure these parameters that are here in equation. And this is a constant, and this is a constant, this is 2. This is sort of a value of electron. This is the parameter. And then this one can be measured in an experiment. For instance, if you measure the mobility of electrons, so we can extract this parameter or some other things. In fact, in very old days, when there was no ab initio simulations, so this measurement, in fact, this was the way to come to this function. Measure this, and then try to recapitulate, reconstruct the function itself, not the other way around. Very good. So very good, very great. So band-to-band transitions. And by the way, one more point. I know that there is also confusion with this from my experience. So if this is, now we're going to talk about band-to-band transition. So there are bands. Say this is conduction band, this is valence band, and this is K vector. So where we can see immediately where there are electrons, where there are holes. So here we have, of course, orbitals where we can populate electrons, as we also discussed in this course. So here we have orbitals, and there are also electrons here, correct? There is nothing else in the crystal. But these electrons, they're exactly those that we look at. When the curvature is like that, this parameter has a negative value. So it means that actually holes are already here. And that can be already at zero temperature, because fundamentally the nature of holes is determined just by the shape of the energy function. But we cannot really do any measurement before we heat this material a little bit, more than 0 Kelvin, so that some of these holes can go up to here, and then they leave empty orbital, because before there is an empty orbital here, there is no transport. There is no way to assess these particles. They are already holes, actually, but we cannot read them before we have at least one or several orbitals empty, because only after the orbitals getting empty, the rest of the particles can start moving, and we can experience this interesting property, that these particles moves along with the applied field, like if they are positively charged. But anyhow, we can have these band-to-band transitions in semiconductors. It can be more complicated drawings than this one. You can also align it with the real band structure, with Fermi-Dirac distribution, to put the Fermi energy here, or Fermi level. So many things can be done, and this can be calculated. But this is what actually I was after, that in order to really to see, to read the properties of holes or electrons, we should supply some temperature, so that some orbitals here gets empty and some orbitals here gets filled. Then basically this one is this part, and these electrons, they are somewhere here. So initially, but maybe I made a little bit a wrong drawing. So initially there are no carriers here at all. So there are just empty orbitals. And then we need temperature to get this orbital occupied and this orbital to be empty. Yeah, this can be very accurately calculated, all these things, and we can see how transport is taking place. But by the way, this diagram is very big simplification. So you see, this is probably what you see in many books, a diagram like this. Usually you don't see these ideas of negative effective mass. What in the primitive interpretation, okay, there is a break of orbital, there is a hole, so to say, correct? And then there is a absence of electron here, effectively positive charge. And this positive charge starts to move. But of course, there are no moving positive charges. It's only electrons that are moving in the crystal. But this motion of electrons is interpreted in terms of a positive charge motion for making it sort of simple. And then, of course, many complicated equations can be written. So you can calculate concentration of this from density of state and product between density of state and Fermi-Dirac function. So I really don't like to pay so much attention, at least during the lectures, to these equations, because they're still complicated. Maybe not every one of you using it every day. But anyhow, we can have these band-to-band transitions. They can be indirect or direct. That I think you know pretty well. I don't really stop here. And then we can make integration of the equations we just have had on the previous slide, and then we can introduce integration of these equations. And then put Fermi-Dirac distributions. I apologize for so many equations, but the final result would be that after integration we can get, for instance, whole concentration as a function of basically as a function of an exponent with a coefficient here that has a much weaker temperature dependence comparing to the exponent here. And the same can be done for electrons here. So we have effective density of states times an exponent. I think what you use in semiconductor physics most are these equations actually. But they are results of integration of all possible states. Okay. Then one can also calculate where this is going to be, where the Fermi energy or Fermi level is situated. For instance, for pure intrinsic semiconductor, it is almost in the middle of the band gap. Let me ask you a question. Why do I say almost in the middle of the band gap? So let me put it like this. Amount of electrons, if you have a pure semiconductor, amount of electrons and amount of free charge here and the amount of free charge there, they should be equal, because should be electron neutrality there, electrical neutrality. But what do you think the Fermi level of intrinsic semiconductor? Is it exactly in the middle of the band gap, or it depends, or it can be here or there? Do you remember this idea? Where is this level? If you look on these equations, so basically this exponent and that exponent, if this one would be exactly in the middle, if this one would be exactly in the middle, then this one and this one, they exactly equal. But the problem is, if you do it like that, then here we have, if you go back to equations here, so you see in this constant here, we have effective mass for carriers that are here, effective mass for carriers for holes that are here, and here we have effective mass for electrons that are there. And we just learned that the magnitude of the mass depends on the curvature of the band. You see, this curvature is in this diagram is much sharper here and much smoother here. So it means that effective mass here is going to be what? Which effective mass? Would be this or that effective mass bigger? This is the question. Can you think? I have carriers in this band and in this band. In which band the mass is going to be higher? Discuss please in small groups. And remember that mass is determined like this. I have to derivate this curve, and that's it. So think a little bit like that. Here I have this band, here I have that band. In what band this parameter is going to be bigger? Can you please think and discuss? So you can think like that. If I have a band like this, so this is k squared, and I have like that. What is going to be, which curve is going to be more inclined? And then depending on this, I can get a value here or I can get a value there. And then I take a reciprocal one. Okay? You understand what I'm saying? Yeah? Then what is the answer? In what band I'm going to have more heavier particles, in this one or in this one? Yeah, so let us go through. So if I have a flat situation, then and if I have this situation, what derivative is going to be bigger? Second derivative. This is bigger, I agree. But then when I switch it, then this is going to be smaller and this is going to be bigger because I switch it here. Yeah. Yeah. So it's and then you see, even I want to put even number of carriers here and there, charge, number of this and number of that in intrinsic material is equal. The Fermi level is going to be switched a little bit in order to make these exponents to compensate for this small difference in effective mass. It's a small point, but it's good to know. It's very easy to measure your knowledge on points like that. Okay, so then I switch to this, and of course, okay. So we can dope our material. So this is what we just discussed now. So we have exactly the same amount of charge in the valence band and conduction band. This is a situation of intrinsic semiconductor. And then how to reach this situation? Yeah, we dope. We want that Fermi level is no longer in close to the middle of the band, but it's closer to the conduction band. How to do that? We put some useful dopants inside. You know that. I know you know. But this is a formalism. And you can do it exactly the other way around. What we are going to do, I know you know that, but what we are going to do now, we are going to show or demonstrate which what kind of impurities are really good for having this situation. What impurities we have to put in, what type of impurities. And these are called hydrogen-like impurities. What is hydrogen-like? What is hydrogen? Hydrogen is this, correct? Hydrogen, we have a charge of the core, and we have electron revolving around. This is a hydrogen. And when we have, for instance, if we have silicon and we have phosphorus atom inside the lattice, we have phosphorus is like silicon almost, but there is one extra electron revolving. So there is a big similarity here. Then what we can do? Maybe in some process, some long ago, you have calculated what is going to be energy of electron in hydrogen. What is the spectrum of the energy levels in hydrogen? This is how is it calculated. It's so-called Bohr model. What is done here? You actually equal potential energy. This is the potential energy of electron on the orbit, and this is kinetic energy. And these energies are equal, it just rotate around. And there is one fundamental assumption. This is often also cause some confusion, that so-called angular momentum is quantized. What is that? Again, from my own experiences, is very confusing. Why angular momentum is quantized? We can talk a little bit about that, maybe. We don't have so much time. I really want to go through these slides. But is anybody aware why angular momentum is quantized? Maybe no. So angular momentum is there. So this we have is here. We have this situation. This is angular momentum, and it can only have specific values of this kind. This is an interesting question. I even, before coming to the lecture, I even was thinking a little bit how should I explain it, because this assumption you need to really to calculate to come to the result that orbits in a hydrogen atom are regular. So the electron cannot really. So you see, it's just this orbit, and then the next orbit, and then another orbit, but there is nothing in between. So the energies are quantized. But the question is why they are quantized. It's kind of a postulate. But it can be explained by the idea that this value is quantized. And what is this? Electron is moving. We believe in that. But it's not really only a particle. So when it, say, imagine this is orbit. But electron is not only a particle, it's a wave. So it is moving like that, correct? So maybe it's not perfect. Let's say we have this one. We can have also another situation that I don't know. We can think that electron is moving like this. I mean, some more. It's a bit art now. Yeah, but by the way, I didn't forget our conversation at the dinner. I'm going to show some pieces of art also later. It's not so good art. But what I'm after is, if this is an orbit, and we have some, we just have to put some number of lambdas here. So if you have an orbit that has this length, correct? This is a cycle. It has this length. then actually the postulate is that in this orbit, we can have only a specific number of wavelengths for electrons. So this is a fundamental assumption. So that, or maybe even not an assumption, but it actually tells us that I think this is already very reasonable. If you have an electron, it moves, it rotates, but it is also a wave. And if it, for instance, goes from here, it should come exactly here later on. So there should be some integer number of waves inside the path of electron. I think this is reasonable. It's like, okay, it's like us. We wake up in the morning, we go somewhere, and in the night we go home. We always, that's our cycle. The same for electron. It can move very fast with different maybe wavelengths, but still it is discrete. It goes home later on. This is quite nice assumption. And then to come to angular momentum, you need just one more step. Really, I think this one is great. I think this idea that we always go home or somewhere where we like is okay. So we just have an integer number of, I don't know, of what. For electron, it's wavelengths. But what is another thing is so-called that any moving object has a wavelength, and this is so-called de Broglie postulate, that anyone who is moving has a wavelength. Electrons, photons, people, everyone, everything that is moving has a wavelength. It's a duality principle, and this wavelength is equal to that. So you can check immediately. So if this is H, this is MV. So if you plug this one inside here, you will get this one. So that is the reason of angular momentum quantization. But anyhow, after you calculate this hydrogen atom, so what you can calculate that the first orbit, the first excited state has this big energy. This is a very famous number. And then what I'm saying is, and what I said, that here is hydrogen. So electron here, it has more than 13 eV in energy. What is going to happen with this electron that is rotating around phosphorus? So this is hydrogen light. What is going to be different? So this is the equation. What should we change to? This equation is for hydrogen electron. What should we change in this equation to adapt it to the electron for phosphorus inside silicon? What we change immediately? We change the mass. From gravitational mass, we change it to effectiveness. This we already know. And then the dielectric constant, this is vacuum, so we have to put permittivity here. And then this value is going to change dramatically. So you see, if you plug, instead of mass, we plug effective mass, and here we add also, for instance, for silicon, we add also this permittivity. So then, if you calculate it, then instead of this much energy, we got this little energy. So it means that if I draw it again, these bands, this is a conduction band. So then, somewhere here, I'm going to have a level, and the distance here is going to be just on the order of 0.05 eV, which is actually quite small. So this is a direct calculation, actually very easy calculation after all, of the donor position in a semiconductor. It is totally based on comparison between hydrogen atom and hydrogen-like atoms. So this is for hydrogen, very nice equation. So we exchange to effective mass, we plug in dielectric constant, and then we have to multiply this with a factor. And this factor brings the energy quite much down. And if you dot with this type of particles, so we have electrons just ready to be supplied to the conduction band when the temperature goes up. I know that you know that. So this is what is happening. This is sort of zero temperature and this is high temperature. When electrons get excited to the conduction band and the Fermi level went out of the intrinsic position closer to the conduction band edge. So this is what is happening. Yeah, now I'm going to do what I promised you to do, to show some art. So this is not really related to donors and acceptors, but it is related to defects, and it is related to semiconductors. So this is a typical solar cell. That is solar cell principle. You know how solar cells work? It's a die. You shine on that, carriers are generated, and get separated. You get current. What are the two major ideas how to improve the efficiency of this device? Basically, you need either increase absorption of the light, or let's say decrease reflection, or you should increase the lifetime of the carriers that are being generated, so that all carriers are taken out of the device. Yes, this is how it works. And now I have the next slide. Here, it's not a solar cell, but there is a similarity of the principles. Have anyone been to Paris? Not yet. Oh, you've been to Paris. Good. Did you go to Orsay Museum? Very famous Orsay Museum, where very famous paintings are displayed. You can see this painting in Orsay Museum of a very famous guy, Claude Monet. Actually, this painting, he paints exactly the same building during different period of the day. I think this is evening, this is day, and this is early morning. Or maybe this is early morning and this is evening. This is day. He painted. How can he do it like that? That he has exactly the same building, exactly the same paint, but of course he put some different colors. But you know what is different here? Very significantly different. Texture. So he put really the volume of this is, if you come to the canvas closer, go back to the Museum d'Orsay and come closer, you will see that the texture of these paintings are very different. Because we have to get a perception of one type of, there is light coming on the painting. So the texture should be such that we think it's morning. And here the texture should be such that we think that it's day. So the principle is exactly the same. He put this very famous painter from beginning of last century, yes. He painted it that way that he put different texture so that reflection of light is different. This is what we did recently with solar cells. We also put different texture so it reflects less, or basically we need less reflection. I was actually very much inspired by this painting before doing this work on solar cells. So this is where, there is a connection between art and science, that we can get inspiration. So for instance, this is a very sort of mirror-like silicon wafer. It almost reflects 50% of the light. You never make a good solar cell of a normal silicon wafer, because then you lose 50% of everything. So what you have to do it texture. The normal texture is pyramid-like texture. very easy to do. You put it in a solution, and instead of a mirror-like very nice surface, you got so-called pyramids. This is done in a Kuocw solution. But still, you see, it's a lot of light that is reflected. Maybe 10% of light is reflected. It's a lot. It's a lot of loss. How to do that? We get better absorption and less reflection. There are methods. There is even a material called black silicon. Maybe some of you heard about that. It doesn't reflect anything, but it is so bad. It's really very difficult to do junctions on that. So basically the clue is we need texture like that, but that would reflect less. And that actually it was known that what can be done are so-called inverted pyramids. They outperform normal pyramids. It's a different type of texture when pyramids looking inside. It was known before us, but we developed a method that is used now. It's almost no reflection at all. How to do this texture, not by very complicated means of lithography, but also just putting wafer into a solution. But it's a more complicated solution. It's a solution with some nanoparticles. The mechanism is also interesting. These nanoparticles, because of different potential in different directions of the silicon wafer, these nanoparticles, they block some etching directions and open some other directions so we can get this nice texture. So this is just an example of other type of defects. We don't need just to look into electrically active defects and forget about the rest of the world. World is beautiful. There is art, there is something else. Open your mind. So really, sometimes you have to open your mind. Even it can get you puzzled, because now you can get puzzled of this example. It has not so much with real semiconductor physics to do, but I promised that I'm going to show something like that. Now we go back to our N and P type material. But this you know very well. So if you have intrinsic material, you have equal concentration of electron and holes. And as we just learned, with hydrogen-like impurities, you can get either dominating N-type or P-type conductivity. So that is very nice. That is shown here by many more electrons and many less holes when you have a donor level, and other way around, like this. This you know very well. I'm pretty sure about that. Correct? Yeah, you're experts. And then it can be generalized like this. We have intrinsic material. We have Fermi level just close or almost in the middle of the band gap, equal concentration of electron holes, and N-type and P-type situation. Everything can be calculated, not so difficult. Like this equation always holds independently on N and for P-type material. So this you all know. But what I wanted to discuss is probably this. Or maybe this is easy for you. This is for less experienced students. But maybe you don't need. Yeah, maybe we can just come to this flow. This we already discussed also, that if you have a doped semiconductor, we will have a carry concentration. So it's N-type material. We will have it like this. First, we have a ionization of carriers from the donor level. Then we have doped situation, N-type, and then here we have intrinsic situation. And it can also you can also read it from Fermi level position. First, we have, it means here we already have the Fermi level you see is already close to the conduction band. It means we have some carriers generated already over the equilibrium situation. But then here, it's a little bit schematic here. So of course, at some point we will probably have a constant Fermi level here. But then it will obviously decrease to come to the intrinsic situation. Yeah, very nice. Then probably I'm doing it fast now, but you see, you know it. What I really want to talk about a little bit more in details is not about equilibrium situation, but when we go out of equilibrium and how we can do that, and what is going to be what are going to be shapes of Carrier profiles when we have these non-equilibrium conditions, and how we can describe it. Yeah, the most simple thing is diffusion. If you have, it actually, I heard from some, in my university we have Department of Physics, and professors are working, professors in astrophysics, like me, semiconductor physics. But there is one topic that everybody likes, is diffusion. I heard from these guys studying astrophysics that galaxies, they diffuse. I don't know if it is true or not, but I would believe it, because this is really probably most general phenomenon, or one of the most general phenomena in the world. If you have a concentration gradient from here to there is no way that diffusion just has to stop. There could be other forces that probably stop diffusion, like in for instance, P and I. But diffusion is always there. If there is a concentration gradient, there should be diffusion. This is a very universal phenomenon. High particle concentration, low particle concentration, we have diffusion. And then how it is going to be then with semiconductors. So if you have a Carrier profile like that, and by the way, how can we create this Carrier profile? It can be just different doping. We probably have a doped material, doped to this amount, to that amount, to this amount, that we have a stationary Carrier profile, correct? It can be also created by illumination. So for instance, imagine that you illuminate from that side. You have more carriers, where you have more excitation and less carriers in the bulk of the material. So there are different means to create this type of things. But as you can imagine, you're experts. These are very important. Then we have to analyze what is going on. Then we can see that diffusion is governed by Fick's law, correct? This is, you have a concentration gradient. This concentration gradient is going to result in a flux or current. And the constant that stays in between is just diffusivity of, in this case, electrons. And this is, if I wouldn't have this, then I would put simply flux here. But because I've put carriers, charge, for each electron moving, I have one carrier transfer. So this is what makes this charge converts flux to current. And you see, there should be a minus sign here for the flux, but it disappeared because this is negative for electrons. And the same here, we have gradient, we have diffusion constant, and we have plus sign. And this minus comes from the Fick diffusion equation. So it tells that diffusion is going to be this way. It goes to equilibrize the gradient. This is this minus sign. Very, very nice. Diffusion is very nice indeed and very general. And of course, you can write then currents in case that you have diffusion currents and drift currents. I don't go in this many details on that because you should know this. This would be a Venn diagram of let's say of a situation when we have more carriers here, correct? Here we have more n-type, and here we have less n-type. Basically, this Venn diagram is reflecting, for instance, this carrier profile. So here we would have more carriers, here we would have less carriers. How is it reflected in the Venn diagram? Yeah, here we have more intrinsic material, here we have more doped material. So then we will get band bending. So this carrier injection it results in band bending. This is very interesting phenomenon. So you see, you can bend bands just by injecting carriers. Isn't it very interesting? And then just as a starting point, starting point for the next lecture and finishing for today. This probably a little bit. Yeah, of course, you can calculate all this because these concentrations, they have temperature dependence, so you can put it into, can make a derivation of that, and of course can have all this calculated. But what I want to come to is you can do it by different means. This generation, you study it by yourself. I want to come to here. This is where we are going to start next time. So this is really also another miracle. Maybe this discovery you already did in other courses. So you see, here we are going to put together not a situation where we have not only gradient in carriers, but we are going to have two different materials. So when we are going to feed material with this low Fermi level and then high Fermi level, and of course we have to feed. We can calculate as it was done here, electron concentrations on both sides. So for instance, holes. You can get the material with band bending, not necessarily going from p-type to n-type. N-type also can be bent by supplying more or less carriers. But the most intriguing and radical situation is when you connect N and p-type. We are going to discuss this in very details next time. Constant periodic solids. We made an introduction during actually 2 lectures, very long one, but I hope it was useful to remember, to recap some understanding. So what is the plan for today? This is our 3rd lecture, and the plan for today is to look into semiconductors. We start with semiconductors today. I hope that you know most of the things in this list. But let me recap that together with you. And before we really start with this plan, I still want to complete one topic that we haven't completed during the last lecture, and that is introduction of effective mass method, because we are going to use it in semiconductor physics. And what effective mass is about, and where have we stopped last time? Let me remind you. I'll remind you briefly. So we are watching electrons. We want to know properties of electrons. Knowing properties of electrons means that we should know energy of electrons. And there are several models, of course, calculating energy of electrons. But the most accurate model is when we consider electrons as waves, because they are really waves. Then the energy can be calculated like that. This comes from solving Schrödinger equation for one electron, considering only kinetic energy in the crystal for electrons. And then we can plot this function energy as a function of k. K is a k vector, and let me plot it with a dotted line. It's like this, correct? And then what we said, this equation only considering the fact that, or assumption that electrons are moving in a crystal without really colliding with the lattice. There is no interaction for electrons with the lattice. Then we get this equation and can calculate actually quite many properties. But what we said, this was our big achievement, but still it was our first step. And the second step was, we said, okay, this is a good approximation that electrons are moving without colliding with the lattice, but probably not sufficient, because we know from all type of waves that if you have, say, if it is our reciprocal space, basically this one, but if I draw it just as a space, for instance, we have two-dimensional crystal with, say, two reciprocal vectors here, k1 and k2, once we have a lattice like this, two-dimensional lattice. It will have a Brillouin zone like that. This is our Brillouin zone. And if the distance is a, then this point would be phi over a. And this point would be, say it is cubic lattice with a distance in all directions, then this is also pi over a here. So if our vector, if our electron, so this is our electron, this k vector k. If k vector is small, if it is not touching the Brillouin zone, if energy is small, then this approximation is fine. We talked about this last time. So I spent so much time on that. But this was for a reason, because now we can use these ideas. So if energy is small, if k vector is small, it is not interacting, it is not really interacting with the crystal, and it's really moving just through. It doesn't see atoms. But if vector is getting bigger, if it comes to the edge of the Brillouin zone at any position, anywhere, just it comes to this edge, so to say, then something new is happening. What is happening? Diffraction is happening, and then we have an interaction with the crystal, and then this model is no longer good. So then exactly in these positions of k, we have interaction of the waves with the periodic lattice. And what is happening, we have also had a model for that instead of this curve, we get in a curve like this. So exactly in these positions, we have these funny deviations from free electron theory. So we have interaction with the crystal, it should be symmetric, of course. Exactly at these positions, we have interaction of electrons with the crystal, and here we have a band gap happening. Yeah, and then we have to find a new equation. Obviously, this initial parabolic line is very nice and simple and great, actually. Really just parabolic equation, so easy to work with. But when we have a curve like this, how can we describe it mathematically? Is a problem, correct? So isn't it true? I have had a dotted line like this. Break this equation. What should I do now? All these complicated, actually really complicated lines, like this, like that. It's definitely not obviously parabolic immediately, correct? There is one method that is called effective. Oh, why I have this? Oh, it's me who moved it. Oh, I thought it was a ghost that moved it. Why? Yeah, I wanted to have just this one. Yeah, effective mass method. What is it about? It is about that, indeed, we know that what is the essence of this method? Maybe you have heard about this. At least you have heard about effective mass, correct? That's something that you use in calculations when check mobility, for instance, or current for electrons, everything. It depends on so-called effective mass. Why? Yeah, because electrons, they're interacting with the crystal. The question is, what is the interaction? What is the potential that, for instance, this is an electron, and it interacts with atoms. What is the potential? Is it a pure Coulombic potential? Is it something else? Nobody knows. The problem is complex. But there is a way to go around that, and this is called effective mass method. What this method is about? Yeah, we know that there is no interaction between lattice and electrons here. And we know that there is interaction in these places. What we can do, if you don't know the function, are you aware about the mathematical trick? If you don't know a function, how can you try to approach it? There is one trick, but this trick is only possible when we want to find function in the very close to so-called critical points. If you have a function like this, for instance, and okay, we have some function, but we don't know what the function is, but we know that this is a critical point, max or min. Then we can do, what we can do, we can write this as Taylor series. I don't know if you may not remember this from maths, or may remember, but any function can be expanded in the following form. So, it should be can be only done around the critical point. So what the function is? For instance, we want to find the function here. So then we just take exactly, we don't know it, but we say we have a function in this point. So what we want to get is a new function as a function of k. And then we say, and we expand it in Taylor. Then we have this function at k equal to pi over a. Let me call it, for instance, just ko minus, what should be the next? The next, do you know that? Anybody know? Anybody remember what Taylor series is? Maybe no, because it was so long ago. But then we have the first derivative of this function in respect with k multiplied by k minus ko. And then we have the second term. This plus sign was minus sign. It is half multiplied by a second derivative over this multiplied by k minus ko. And then we can have many more things here. 1 over 6. Basically, it's 1 over m, and then derivative of Don't remember 1 minus n maybe was a function in respect of this. So this is a part. There is a series. You don't need to be scared by the math. We just stop here. We say that there are other terms, but we neglect all these terms. And once again, why this is working for any function in the vicinity of a critical point, max, or mean. Let's look on that. This is just a constant, correct? It's a number. It's a value of the function in this position. Constant. Basically, we can actually put it either to 0, or we can say this is going to be the bottom of the top of our valence band. But for simplicity, we can put it to 0. Then, because we always can adjust the 0 point for energy. This term is actually 0. It is equal to 0 because we have a critical point, and in a critical point, first derivative is always 0. Then we are left only with this term. So then we can write, in this complicated situation, instead of that, our energy is equal, at least can be approximated with this function. And then, I forgot one important thing. It should be squared here, of course. Then we also can put, we can also calculate k from any position. We can just put this to 0 too. So then we have this expression. You can start guessing what is he doing. He doesn't know this function, and then he expresses the function as a second derivative. If I don't know this function, of course I don't know this. You can think, oh, this is nonsense. Do we have a progress? Did we do anything? Mathematically speaking, no. But we can think a little bit about physics. But first, before we think about physics, let's be a little bit, so to say, stupid. If you look on these two forms of equation, so here we have energy, here we have k squared. So here we have energy, here we have k squared, and this is a constant here. What is the difference between these constants? So if I try to say that in what case this is going to be equal. So if I have this is equal to 1/2, and then I have this derivative. So then, basically what I want to say is that how can I make these two things equal? Or not equal, but looking similarly. So if I put in a new parameter called effective mass in this equation, and if effective mass is going to be equal to this, correct? So if I put this one in there, then I'm going to get exactly this expression with a different symbol here. Correct? So you see, if I exchange this one with the mass, then I'm going to get it identically written. So if I have this definition of effective mass, a parameter, then I can write these two things very identically. I can write it like this, that this is 2, m, but effective k squared. Do you agree with me? So if I just define effective mass, something that I call effective mass in this way, then I'm going to have very identical formula. So you see, this is a situation when electrons don't interact with the crystal. Small k, just like this. If I have interaction, I still can write a very similar equation, but then I have to exchange mass with another parameter that is called effective mass. Why? Yes, that is because in this case, electrons moving in the crystal here, they don't interact. They have a kinetic energy, correct? What is kinetic energy? How do we write it? It's like this, correct? So they have their velocity only because they just move by thermal energy. But here, these masses, they are not only moving because of thermal energy. They also interact with the lattice. So this is why we introduce this. But once again, do we know this effective mass? What is the effective mass? Yes, indeed, from physical point of view, from mathematical point of view, if you don't know the function, you will never know the second derivative. Because to get the second derivative, you have to derivate the function. But the thing is that in many cases, we can experimentally measure effective mass per meter. Why? Let's see, let's check. What I'm going to ask you now is to make an exercise in these small groups that we usually build. So I draw it once again. And what we are going to do, we are going to try to solve this concept geometrically, so to say. If this is our pi over A, this is where electrons interact with the crystal. This is pi over A. So you see, these are very important points. So if you would have no interaction, then we have this situation. But if you have interaction, then we have this situation. Sorry. And then we have this situation. But that's my take. It's enough for the first result. So then imagine, so this is our energy as a function of k. But let us continue and analyze graphically, qualitatively, if we are going to differentiate this curve, this red curve now, if we are going to differentiate it first time, if I want to find this qualitatively, how this function is going to look like. I want to differentiate this red curve first time. And I know that this is parabolic, and I believe that it's also parabolic in these parts. Let me show you what I mean. How the first derivative is going to look like. When I differentiate, say, this is almost parabolic, correct? So when I differentiate k squared first time, I'm getting just k, correct? So here I'm going to get a straight line, just around the center. Maybe it's better to use red. So I'm going to get a straight line here, correct? Here I also have parabolic, but it's a different curvature. So So these are these points. So you see, it's a different Kuocw here. So I'm going to get a straight line too, but it is going to be directed this way. And here I also have this Kuocw, so I'm going to get this straight line. So the result of derivation of this function qualitatively is going to be straight line here, some connection here, straight line there, some connection here. This is the first derivative, correct? Now, you are going to do the second one. So derivative, please. One more time. So we are after the second derivative of this function or first derivative of that one. How this is going to look like? Please. On your own or building groups, discussing, it's up to you. I give you 3 minutes to do that. Or maybe 3 minutes is too much. 2 minutes. You are so clever. So you understood what I asked you to do? Very good. So, what is going to happen? How we do second derivation of this function or first of that one, and here, but basically I think you already know. So we probably should also get some points from there. What is going to happen is that I have just line here. When I derivate the line, I get a constant, correct? He is a constant. What is going to happen with this line? If this line has this tangent, it's a positive, but this line is negative, correct? It's going to be here. Yeah, and then it's fine, it's a good function, no problem, so it is just this one. And then finally what I want us to do is, because we determined effective mass, not exactly like first derivative, but as inverse first derivative. So can you please plot as a final result, plot effective mass as a function of k. And effective mass is here. It's just inverse value of this plot. Can you please try to make this discovery now? How the effective mass look like? And this is absolutely correct. If you didn't know it before, this is going to be one of the greatest discoveries that you did in this course. Because what you should come to, of course, when we have a value, and basically when we switch value, I mean, to 1 over the value, so the sign is going to be the same, correct? If I have had a positive here, I will still get a positive value here, and I will still get negative value here. But I will not be able to actually get it connect. So it will look like that. So it will go to infinity here and there. It will look like that. So that is a plot of the effective mass. You don't look like you made the discovery, but isn't it a little bit interesting? I don't know if you ever heard it from anybody else. What happened? We have a parameter that connects. Really, it's here. It is here. It connects energy with the K. It's energy. It's what we want. But for some electrons, we have this parameter normal, at least it is positive. We know that mass is positive. But for some electrons, this parameter became negative. Have you ever heard about this? We have some electrons that have negative parameter connecting energy and K. It's fantastic. At least it's some it's almost irrational, correct? We have a parameter that should be positive, but it is negative. Why? Yes, because it is exactly because of a very, very strong interaction in these parts. So what we see from here is that in our system we study electrons. This is what we do, electrons in periodic solids. Actually, we have two types of electrons in the crystal. Really, by far, we said, depends on the K number, we can have interaction or we can have free electrons, correct? So if K comes to the Brillouin zone, we have an interaction. If it is not coming, they just flow freely. But it's sort of qualitative description. But now we have a fantastic quantitative description. So you see, this is a K number, K value of electrons. When K is small, we really have normal electrons. Normal, at least with positive effective mass. When K is big, we have really abnormal electrons. They have negative effective mass. It's almost irrational, it's uncomfortable, it's not really nice. Or at least it depends how you see discoveries. But I see that you are a little bit confused. Yes, these are very abnormal electrons. And in order not to really get it confused all the time, so what is done in semiconductor physics, and that is probably you just learned, never thought about it, why? We call these particles electrons, and we call these particles holes. And in order not to confuse ourselves with effective mass that is below zero, and these are electrons actually, yes?
Shouldn't the second derivative graph should be flipped upside down?
Yeah, but then we do like this.
We have the same graph that we're doing.
Huh?
So the third one is right and the second one should be
This one? But if I, maybe I should do it like that. Then it is fine. Okay? Yeah? Sorry. But it's good that you watch me. Now I think it's correct. But very important thing now, really. In fact, if you should be aware that there are no positive charges in materials. When somebody tell you that there are holes and holes are positively charged, it's a fake. There is no reason for having positive charge in materials. There are only electrons. But the thing is that this is a discovery, that what we learned now, there are two types of electrons. One, normal. They just behave normally. The other one, having bigger K numbers, abnormal. And they have negative effective mass. In order not to make it too much confused, we say, okay, these electrons are abnormal. They have negative effective mass and and of course negative charge. They are electrons. But in order not to follow with this, now you are educated people, you know that. But before you came here, or maybe some other people, they cannot imagine negative mass. Then, instead of following this, what we do, we say, okay, we say that these electrons are having positive mass. But then we have to give them positive charge also. to let them to be affected by the field, like they have negative mass and negative charge. So it's just a trick. There is no physical meaning in thinking that there are positive charges moving in the crystal. They are not. They're just not there. It's like I would say, okay, Kan Hun. He's not here, correct? Do you know Kan Hun? You maybe I pronounce Kan Li, Kan Hun. He's not here. He's not here. Is a fact. The other fact, in the sample, there are only negative charges moving. It's no way you get positive charges moving there. They are not available. Only electrons. But there are two different types of electrons. One having this parameter positive, the other having this parameter negative. But not in order not to create confusion, then okay, we say let this particle also having positive mass. But then we have to assign them also positive sign, so that they are moving. If I imagine if I put electric field on a sample, if I have these electrons, what they are going to do? They have positive effective mass and they have negative charge. Of course, they will move against field, because we put the field, the charge is negative. The velocity will be against the field. For normal electrons, this is a potential. The velocity is going to be in this direction because the charge is negative, correct? But these particles, they will behave differently, because if I put these particles in here again, they have negative effective mass and they have negative charge. Then the direction of the particles will be not against the field, but it will be along the field. Like if these particles are positively charged. But the essence, the truth, the very, very truth, there are no positively charged particles. It's only difference in mass, in the sign of mass. This what I call a discovery. I hope you made a discovery. This is very important, because now we know that there are two different kind of electrons. There are really electrons, and there is something else. And this something else we call holes, because they behave like they would have they have negative mass, negative charge, and then they move along the field. But they behave like they would have positive mass and positive charge. So that's why we call for two different types of carriers in specifically in semiconductors, because this specific behavior is very typical for semiconductors. Right. I hope you liked it. Or okay, my proposal is, this is what I usually do for my students, because from my experience, this is a shock, that something has a negative mass. This is a shock. So probably you need to discuss it in small groups for 1 minute, exchanging opinions. Of course, this is true, but talk a little bit, what do you think? Yes, this, from my experience, my own experience and experience of my students, this is one of the greatest discovery you can do with very simple theory, because it still agrees. We don't really do theory. We just made a graphical interpretation of the curve. So you even was so accurate that you corrected me that I made it wrong. Thank you so much. Yeah, it just really just derivation of a parabolic function. But it brings to fundamental conclusions. There are two types of carries, and this depends on where k vector of these carries are. If it is small or if it is big. Right. Very good. By the way, of course, I have to. I think you intuitively already completely understand it. This is really not a gravitational mass. It's not a gravitational mass of electron. It's a parameter in the equation that behave like the mass. And why it is so? Yeah, because I just try to visualize it here. Because electron, as I also try to say, it is moving not only because of kinetic energy, but also because of the interaction with the lattice. And this actually parameter, it's basically, you see, what is this parameter? It's just second derivative of energy. So it actually contains all information about interaction between electron and the crystal. And at some positions of K, this can be negative. That's just a parameter. But we call it effective mass because it brings so excellent similarity between this equation and that one. Okay. Yeah. We just, I don't think I will talk about this. But what I can talk, just one comment. You see, if you have, for instance, a crystal. Because, okay, this is fine. This is for one-dimensional situation. But imagine you have a crystal having two different lattice parameters in two different directions, which is actually quite normal. Correct? Most of the crystals, they are not really so cubic. What is going to happen? So you see, this is a plot for this direction, and this is a plot for that direction. So what can happen? You see, the magnitude of k in this case is pi over a. So a here is big comparing to b. So it means that this distance is smaller and this distance is bigger. But it is happening in the same lattice. So it's if you have an electron, we cannot tell him just watch this direction or watch that direction. It is moving in the crystal. It's like freedom, you know. I choose my line. I go this way or that way, correct? But then if, for instance, you see here, if I would have a totally cubic lattice, then reaching to this level, my electron is going to interact with the lattice. Because if it is here, if the K is this big, there is interaction. But this electron, instead of doing that, it can actually choose another direction. You see, this is exactly that value. I bring it here. But here there is still no interaction. So this is what is called, actually, and this is the reason for so-called band overlap. Maybe you heard about this expression many times. Band overlap. What is band overlap? These are our bands. These are really our bands. But one is drawn in one direction and other in another direction. And for an electron to have this K, it would reach a situation when it has to interact with the crystal. But if it will follow this direction, it will still be free. This is actually the reason, really fundamental reason for so-called band overlap. Why, for instance, we have semi-metals? Just because in some crystallographic direction, there is already, interaction. But in some other direction, there is no interaction. This is actually quite instructive to think about that. The other thing is, if this is our function, if this is our effective mass, and imagine maybe you heard this, or maybe you even use this vocabulary, that you may have heavy holes, or you may have light holes. What it means in terms of these functions, in terms of the bands? Yeah, it's very simple. If you have a curve, if you have a valence band curve, broad, then when we derivate it, then we going to get big value here. Oh, sorry, small value here, and then when we make a reciprocal thing, maybe we are going to get a bigger one, and then for this situation is other way around. So everything depends on the band structure. So what is heavy? Maybe it's obvious for you, but I just mentioned that the ideas of different mass for different holes means just the dispersion relation is differently sharp, basically. Yeah, like here, for instance, we can have light holes, heavy holes, depending on the sharpness of these dispersion relations. Yeah. So I suggest after that we go to. I'm going to make a break very soon, but because now we are going to rush very fast, because basically all the rest you know very well. So we are going to work with this topic, and we go through this list relatively fast, because many of you work with semiconductors, correct? I think everyone will study, but we will still go through all topics here, looking into physics, not writing too many equations, exactly like we did it with effective math. We'll probably get more discoveries. So let's take a break. We did a good